Greetings to you all. Today's class will be the last class for this week on this course CFD. So far we have done information about different approximation methods, properties associated with the numerical scheme, then how to analyze a numerical scheme for consistency, convergence and stability. In today's class we will get explanation of these with some more example equations. First, let us consider as in the past 1D unsteady diffusion equation, dou u by dou t minus alpha dou square u by dou x squared equal to 0. We also learned in the previous lecture different scheme available for this model equation. One other thing is explicit scheme and forward in time, central in space. If you write down the difference equation, we get this form u of I n plus 1 minus u of I n by delta t equal to alpha u of I minus 1 n minus 2 u of I n plus u of I plus 1 n by del x squared. We mentioned forward in time. So, the superscript n is between n plus 1 and n, central in space. So, the subscript I which is used for space and it is central. So, we have node of interest I and left node and right node I plus 1 and I minus 1. It is also possible to write different other schemes, for example, forward in time, forward in space, forward in time, backward in space, central in time and central in space. And it is also possible to write different order in any of the schemes and analyze appropriately. Order of this scheme, order of accuracy of this particular scheme is delta t and del x squared, and we already learned this scheme is stable for r less than or equal to 1 by 2, where r is defined as alpha times delta t by del x squared. That is, alpha is here and del t is moved from the left hand side to the other side, and this is alpha delta t by del x squared. This is what we learned through von-Neumann stability analysis. We can also write same forward in time, central in space, but in explicit form. So, we at that time we mentioned what is explicit, what is implicit, and here also we are going to re-emphasize that point. So, this is forward in time on the left hand side for time derivative u of I n plus 1 minus u of I n by delta t. This term is same as what is explained here. There is a small difference on the right hand side term for spatial differencing, and here you can observe it is central in space because u of I minus 1, u of I and u of I plus 1 we consider, but it is implicit, which means it is evaluated or it is considered at the same time level. The time level here is n plus 1. So, all these variables are considered at the same time level. So, you observe the superscript as n plus 1 in all the three terms. Such a scheme is called implicit scheme, and both the schemes you can understand by the sketch here. So, explicit scheme is what is shown here. Value at n plus 1 is evaluated based on values at n level, but using central difference scheme I plus 1, I and I minus 1, and this is for explicit scheme, and this figure demonstrate how it is for implicit scheme. We consider again values at I plus 1 at I minus 1, but at n plus 1 level. Now, we try to understand how to get different explicit scheme. There is a scheme called Dufort-Frankel scheme, which is central in time and space. So, if you look at time derivative discretization, you observe here u of I n plus 1 minus u of I n minus 1. So, it is actually evaluated as central scheme, but in time, that is why you get superscript n plus 1 and n minus 1, corresponding denominator 2 is appearing. And in the spatial, for spatial derivative, it is central in space, but there is a small difference u of I minus 1 n. So, it is explicit. The last term u of I plus 1 at nth level, hence it is also explicit. The middle term is evaluated using central. So, this is u of I n plus 1 and u of I n minus 1. This happens to be unconditionally stable. If you remember or if you just recall, we learned forward in time, central in space is conditionally stable, whereas if you replace one particular term, middle term, by this central in time. So, n plus 1 and n minus 1, stability condition changes from conditionally stable to unconditionally stable, and the scheme also happens to be of order of accuracy delta t squared and del x squared and delta t by del x squared. So, if you compare against forward in time, central in space, where it is conditionally stable and order of accuracy is delta t and del x squared. So, the middle term, which is shown here for the FTS u of I n, which is completely explicit, is replaced with u of I n plus 1 and u of I n minus 1. So, by changing this slightly, you are able to get a conditionally stable to unconditionally stable, and order of accuracy is also improved. You can observe that. There is also a small note to be observed, that is for the same scheme Dufort-Frankel scheme, which is central in time and space. If you observe here u of I n plus 1 and u of I n minus 1, when you are starting the calculation, that is at time is equal to 0 level, for example, then this quantity, that is u of I n minus 1, is not available, because you have not done the calculation. When you say n minus 1, it is before 0 and that time it is not available. So, this particular scheme Dufort-Frankel scheme, self starting at time is equal to 0 level is not possible, as data at n minus 1 level is not available. So, at time is equal to 0 alone, we do the calculation based on any other scheme. Once that quantity is available, then you can switch to Dufort-Frankel scheme. We will move on to the next, that is implicit scheme. So, general discretization for the same model equation. So, this is time derivative, which is forward in time u of I n plus 1 minus u of I n by delta t. There is a small difference here on the right hand side for the spatial derivative. You get two components here, the first bracket term u of I plus 1, u of I and u of I minus 1. So, it is central in space, but on the superscript you see n plus 1 for all the quantity. So, it is central in space, but implicit. Now, we will move on to the next bracket term, that is here. It is again central in space, but it is evaluated as explicitly at nth level. So, you can see all the superscript for all the three terms as n. This scheme is unconditionally stable for value of theta greater than or equal to half. So, we have a factor called theta, which is multiplying one part 1 minus theta, the factor multiplying another part. Now, there are multiple variations for different values of theta. If theta is equal to 0, so that is if you look at the first term, if theta is equal to 0, implicit in time is not there, and you get 1 multiplying the second part of the equation. The second part of the equation happens to be fully explicit. So, for theta is equal to 0, it results in forward in time, central in space, explicit. This we have already seen, and for theta is equal to half 0.5 value, we get weightage, actually weightage of equal weightage of implicit scheme and equal weightage of explicit scheme. Such a scheme is called Crank-Nicholson scheme, because it is proposed by both these people, and it is neither explicit completely nor implicit completely. So, it is referred as semi implicit, and for theta is equal to 1. So, if you substitute theta is equal to 1 in the second term, 1 minus 1 cancels off. So, the explicit part goes to 0, only the implicit part remains. So, it becomes fully implicit scheme. So, you understand, by writing this generalized discretization equation, you are able to get 3 different scheme: forward in time, fully explicit, then Crank-Nicholson scheme, semi implicit, fully implicit also you are able to get. So, fully explicit, fully implicit and semi implicit, all the 3 schemes are possible. Next, we take 2-dimensional equation and try to get information about these quantities. Again, we take explicit, forward in time and central in space. So, you write down the equation. Now, the index for subscript, we have used I for x direction, now use I and j correspondingly x and y direction. So, forward in time, this we already know, and central in space, but we have 2 terms, one for x, another term for y. So, this term in the first bracket is for derivative in x and second term is for derivative in y. We write accordingly central in space in x direction. So, I minus 1, I and I plus 1, central in space in y direction. So, it is I j minus 1, I j plus 1, and it is explicit. So, you observe all superscripts are n. So, all these quantities are evaluated at n time level. You can rewrite this equation by bringing all the known terms on one side and the quantity or the variable that to be determined on other side. So, in this case u I comma j n plus 1 is a quantity to be evaluated, and that is retained on the left hand side, as you can see here, u of I comma j n plus 1, and you bring all other quantity to the right hand side. So, u of I comma j n plus dx one set of term plus dy another set of term. It is also again you can rewrite, because you observe u of I comma j n appears 2 other places. So, you bring all u I comma j n together, you will get a coefficient for u of I comma j n, and then u of I minus 1 j and u of I plus 1 j and the remaining terms. So, this is the way you rearrange and write for coding purpose, and the dx is explained as alpha times delta t by del x squared. Similarly, dy is explained as alpha times delta t by del y squared. Now, let us look at this little more detail. Order of accuracy for this scheme is delta t in time and del x squared and del y squared for 2 different spatial direction. We also learned through last lecture that the scheme is stable only if delta t by del x squared plus delta t by del y squared multiplied by alpha is less than or equal to half. This is what is known as a summed up condition, and we also mentioned if you extend this for 3D, you get one more term here and it becomes restrictive. Alpha is given in that equation, delta t if you fix, then you have a limited option on del x or del y, so that you satisfy stability condition. Now, we can rewrite the same in fully implicit form, still following forward in time and central in space. So, you get superscript on all the right hand side term as n plus 1, which means you are actually evaluating at the current time level. Some of them are not evaluated, some of them are part of the equation. And if you rearrange as we did in the previous case, rearrange all the term accordingly. So, in this case the only term that is known is u of I comma j n. So, you move that to one side. So, that is what is taken here. Then all other terms are brought to other side which are not known, because all are to be determined or to be evaluated at n plus 1 time level. So, you get rearranged and you get this type of equation. So, this particular equation is run through entire computational domain or along a line, nodes along a line. Then you get simultaneous equation. For every node you will get one set of equation and you need to put them together and invert the matrix. So, you get simultaneous equation needs to be solved, because variables at different nodes are coupled with each other, and this set of equation will result in what is known as a penta-diagonal matrix. In the next slide I am going to show what is a penta-diagonal matrix. Usually either you would have a separate procedure to invert a penta-diagonal matrix, it takes definitely time consuming. There is a alternate way of doing the same, that is same equation. We are seeing multiple methods of doing the same equation. The second two dimensional wave equation, sorry, two dimensional diffusion equation. First we have seen explicit, forward in time and central in space. Then we have seen implicit, forward in time, central in space. We understand like order of accuracy as well as stability condition. Now, let us look at different matrices. What is shown here is just a diagonal matrix, only one along the diagonal only one quantity is remaining, all other elements in the matrix are having 0 value. Then there is another matrix called tridiagonal matrix. This will be extremely useful, we will see later how it is used in CFD, because in this the diagonal main diagonal what is shown in the red, there is a value along the main diagonal, then there is immediately there is one diagonal element, one diagonal parallel to that which is called super diagonal, and you have values along that. Similarly, immediately below there is diagonal called subdiagonal and you have values along that. All other elements in this matrix is 0, such a matrix is called tridiagonal matrix. Then we will see pentadiagonal matrix. So, this has the same structure as tridiagonal matrix, that is you have one main diagonal, immediately below is a subdiagonal, immediately above is a super diagonal. Then there is one more column or one more diagonal which is called super diagonal, which is following the super diagonal and you have values along that. Similarly, on the lower side there is one more diagonal, one more line following closely the main diagonal, but just below the subdiagonal where values are available. So, you have a pattern and this is what is called pentadiagonal, but regular pattern. Now, if you look at, it is also possible to have pentadiagonal of different pattern. So, you can see main diagonal is there, subdiagonal is also there, superdiagonal is also there. The next subdiagonal or superdiagonal is not there, but it is after that. So, you get one more line with values, another line with values. Now, why I need to bring this? Because you may get what is known as different block structured matrix for different problem, and solution procedures are different for each of these matrix structures. Now, we will see little more detail about what we mentioned in the previous slide, that is for two dimensional diffusion equation, if you do completely implicit scheme, then it results in pentadiagonal matrix. Inverting that such a matrix is difficult, and there is an alternate way of doing what is known as a splitting, and that is referred here as alternating direction implicit method. So, you solve the same equation, but in two steps. In the first step, equation is discretized and implicitly solved in x direction and explicitly solved in y direction. In the second step, equation is discretized and implicitly solved in y direction and explicitly solved in x direction. So, each time step solution is advanced by n plus half level, which means to go from n time level to n plus 1 time level, it is obtained in two steps. Now, such a matrix results in two tridiagonal matrices, and there is a standard easy procedure available to invert such matrix, and this is easier compared to pentadiagonal matrix. If it is a 3-dimensional equation, we extend the same logic, that is to go from n time level to n plus 1 time level, solution is advanced by 1 by 3 step. So, n plus 1 by 3 and n plus 2 by 3 and n plus 1. So, that results in 3 tridiagonal matrices. Now, we look at the equation. So, first step, equation discretized and implicitly solved in x direction, explicitly in y direction. If you look at the expression for the time derivative, we mention it advances by half. So, the superscript is actually n plus half, then it is implicit in x direction. So, all the quantities which are corresponding to derivative in the x direction, dou squared u by dou x squared. The scheme is central in space. So, you get I plus 1, I and I minus 1 as a subscript, but it is implicit in time. We are evaluating at n plus half, and that n plus half appears in spatial derivative term, that is why it becomes implicit in x direction. So, we have n plus half as a superscript on terms corresponding to second derivative dou squared u by dou x squared, still central in space, and it is explicit in y direction. So, terms that corresponds to y direction, that is dou squared u by dou y squared, you are evaluating central in space. So, we have j plus 1 j and j minus 1, but it is explicit in time. So, we have superscript n appearing here. Now, once you solve this equation, the quantity that will be coming to known is u of I comma j n plus half. So, in the second step, the equation is discretized and it is implicit in y direction, explicit in x direction. So, we switch implicit and explicit directions. Now, we write down the equation. As I mentioned, when you solve the first equation, the quantity that is coming to be known is u of I comma j at n plus half, and that is taken, and we mention it is explicit in x direction. So, if you look at the derivative in the x direction term, So, that is dou square u by dou x squared. All the quantities are with a superscript n plus half, which means it is explicit in x direction, and you have moved, you have actually come to the correct time level n plus 1, and we mentioned it is implicit in y direction. So, the term that corresponds to y direction is here, and you look at the superscript, they are all at n plus 1 level. So, same equation is split. In the first step, it is implicit in x direction, explicit in y direction. In the second step, we switch the direction, it becomes implicit in y direction and explicit in x direction. Now, if you look at the order of accuracy, it is delta t, del x squared and del y squared, and it is unconditionally stable, whereas fully explicit forward in time, central in space still is conditionally stable. So, we get advantage by doing this alternating direction implicit, that is you get matrix simplified from pentadiagonal to 2 tridiagonal matrix, order of accuracy improved and it becomes unconditionally stable. Now, let us understand this by a graphical sketch. So, fully implicit forward in time, central in space, suppose these are the quantity grid and these are nodes and nth level. So, I and j is here, I comma j is here, and to evaluate I comma j at n plus 1 time level, that is what is this plane, we move, we take all the quantities corresponding n plus 1 level. For the same problem, but if you do forward in time, central in space by ADI method, we introduce one more plane at n plus half level, and plane at n plus half level we do x sweep, and then at n plus 1 level we do y sweep. So, in today's class we particularly looked at how to do different finite differences scheme, or how to improve order of accuracy, or how to get conditionally stable, unconditionally stable, and very important topic alternating direction implicit, advantage associated with that. With this class we have come to end of this week, and we have touched upon the initial aspects of CFD, that is basic information about finite volume, finite difference and finite element method, properties associated with the numerical scheme, conservativeness, transportiveness, boundedness, how to analyze numerical scheme, consistency, convergence and stability, and explanation with different model equations. Thank you.